All right, everybody. I think it's about 1 o'clock. That means it's showtime for us again today. Welcome to a new week. I hope that everything is going well and you guys are handling the cold, wet weather out there. It's been a little bit winter-like, I guess, for a couple of days. I tried to go hiking on Sunday, showed up to a trail that was closed. There was all kinds of debris everywhere, and they're worried about erosions and mudslides. So, I guess I'm not doing my hiking this weekend. It's okay. I have plenty of other things to keep me busy. But anyway, hopefully we'll get the moisture we need and then get some sunshine back again. I have a few quick announcements. First of all, there are two things that are due tonight at this point. The first one is a homework assignment, which we are going to do a bunch of the problems. Nobody put any problems on the side yet, but that's okay. We're going to do a bunch of the homework for tonight just to take it off of your plate, basically. That's what I want to do. And so that's one thing that's due tonight by midnight. The other thing that's due by tonight, I sent you out yesterday in an email this extra credit quiz, and it will be worth up to 3 automatic points just added right to the top of your first midterm. So that is also due tonight. I would like to get them in tonight so that I can grade them and give you the feedback by tomorrow. And I'll post solutions and all that so you can review them a little bit. But it's kind of a win-win because if you do the extra credit quiz, you'll not only get points towards your midterm, you're actually going to be reviewing for the midterm at the same time. This might bring some things to mind and kind of remind you of some things to review. So I know it's kind of a double whammy with things that are due tonight, but I think it's ultimately going to be for the best for all of us. And like I said, I will work on a lot of the homework during our class today. We're really not going to do much new material today. I'm going to view it mostly as a review session because we actually covered everything already with just a couple little loose ends. So I'll point out those loose ends as we need to, but then for the most part, we're going to review. I've got some group work we're going to do, and we'll just try to make sure we're as ready as we can be. Don't forget, I have a ton of office hours between now and Thursday. The test is on Thursday right at this time. You guys did a better job than my morning class of actually being here on time. So just to remind you, you're going to have the entire class period. And if you come late, you're going to lose those minutes to take the test. So please try to come a little early, especially if it's raining again on Thursday. Watch out for the traffic and the parking and all that stuff. Just try to get yourself here comfortably so you don't have to stress about that and can just be ready to go. Because I will start right at the start of class on Thursday with the exam. Of course, the resources folder is up. I know some people have already been looking at it. If you do nothing else before the exam on Thursday, at least try one of those sample midterms. Now, by mistake, I accidentally put the same midterm in twice originally into that folder. I didn't catch that mistake until the weekend, but I did fix it now. So there are actually 2 different sample midterms in there. These are just midterms I've given in the past. So you can just take a look at them and get a pretty good idea what kind of things I might ask about. I have not written this exam yet for this Thursday, but you can bet it's going to be along the same kind of lines of what you're going to see in those samples. I would recommend, if you haven't done it already, that you try to get a sample exam looked at before Thursday. And if you try a sample test and you realize that there's some areas you need to review, then I would do that. I try to review that a little bit and then maybe even look at the other sample tests to see where you, if you have improved, I should say, right? Or you could try the review session problems, or you could re-practice the group work. So there's no lack of things that you could look at again. The only thing I will say is I would not try to redo all of the homework again. Okay, there's a couple of students who wanted to do that, and I was like, that's going to take you a very long time. I think it would be better to really work on the stuff that's in that resources folder. So last week I pulled that up and we looked at it in detail. And I really think that's just my suggestion. That's the best way to go to get you ready for Thursday. I want everybody to do well. Obviously, I'm here to help. This is why I chose to do this kind of career, because I like helping people learn math and understand math. So if there's anything I can do in these next 2 days to help get you ready, I really hope that you will let me know. I'll do what I can. Okay. Any questions about any of that? Not so far. So you'll have a chance to get 3 extra credit points on this quiz that I distributed. After the exam is over, next weekend, I'm going to ask you to watch a video. It's kind of long. It's like 80 minutes. So you might need to do it in a couple of sessions, or else order some popcorn or something to turn it into like a movie and just take notes and watch the movie and try to do your best to understand that next set of material. But you will get 4 more points of extra credit for watching that video and taking notes on it and submitting it into Canvas. So that is a definite must do, I would say, for anybody in the class. And you won't have any other homework. It'll just be that for the weekend. So that's kind of where we're at as we get kind of towards the 1/3 mark of the semester here. I did put a recap on the board like I always do. I'm very much in the up with determinants camp. I believe they are awesome and that there's so many things that we can do with them. And I put this list together, everything in one list of some applications of determinants, okay? And we've already talked about most of this. Like I said, there's a couple of loose ends that I need to kind of shore up here today, but it's not going to be anything too heavy or substantial. The first one that sort of kicked off the chapter was just, hey, we can use determinants to see if a matrix is invertible or not. Right? If you just calculate this determinant of A, as long as it's not 0, then your matrix is invertible. This is a good thing to know, right? We'd like to know whether we have an invertible matrix in our hands. Okay, so that's one thing. That's kind of at the top of the list. But then last Thursday, I started mentioning some other things that determinants can also be helpful with. One of them is that if there is an inverse matrix, right? So if the A inverse does exist, there's this thing called the adjoint method for finding the inverse. So this is a way of getting the inverse of A without ever doing a single ERO. We can find A inverse just through this formula here, and you will want to memorize this one, right? 1 over the determinant of A times this thing that's called the adjoint of A, okay? So the adjoint of A, I'm going to put this over on the side, so it's kind of out of the way here. But just to remind you from last Thursday, I did go over this and we did an example, but I just want to remind you. What you're doing here, guys, is you're taking the matrix that is filled with cofactors. I called that M sub C, and you are simply going to transpose it. So you're going to take the transpose of the matrix of cofactors. So that's where you swap the rows and the columns of the matrix that had the cofactors in it. So this technically, this should probably also go in a box. You do need to know that as well. So the adjoint is this just the transpose of the matrix of cofactors. So this is pretty nice. This means if I want to find A inverse, I can just find the determinant of A, put the reciprocal of that in front of the adjoint of A. Easy enough. If I have time later today, I might even try to prove this formula and justify it a little bit. If I don't get a chance to do that, I definitely have a video on it in my resources folder. For those people who don't like to just take equations on faith, that is possible. But for the time being, I'm just going to use it kind of as a free formula. Now, the one loose end, guys, on Thursday last week that I didn't quite have time to finish was this third point in the list. This is something that I only started adding to Math 250B in the last few years because I was having students coming to my office hours that were over in the engineering department, and those professors are expecting the students already know the Cramer's rule. So I decided, well, maybe I need to be explaining that one in my 250B linear algebra class. So this is a method for solving a system. So if you have AX equals B, that's a system of equations, and you would like to solve for the unknowns. Well, this is a way of solving for the unknowns without ever doing an ERO. Let me just take a breath for a minute here, guys, and just really make sure it's clear. We already knew how to do these things in chapter 2. I'm not saying this is anything new here. It's just a different way of doing those things. So finding the inverse of a matrix, we've known about that for a couple of weeks. Doing the system of equations, solving a system of equations, we did that a couple of weeks ago as well. So this is not new tasks that we're talking about. What we're looking at here, guys, is new ways of doing these tasks that involve determinants rather than EROs. And you can be the judge. Maybe at the end of the day, you're gonna be like, I'm kind of down with determinants too. I'd rather do the ERO approach. That's fine, okay? But I at least want people to be aware. Now, the Cramer's rule allows us to solve for the unknowns. Those are the X's that are in this vector. Those are the unknowns of my system. And it's simply one determinant divided by another. So obviously that's just going to come out to be a number. Take a determinant, divide by its determinant, you get a number. And the only thing, and this was the loose end I didn't have time to explain last Thursday, is what is this BJ thing here? So I'm going to put that over here in blue as just kind of a little add-on. This one we did not write down last week, so this would be good to make sure you are getting down. B sub j is really just the matrix. So what it is it's the matrix, I'll write it in words here. It's the matrix A, so you take the original matrix A with the jth column. So this is a column thing. The jth column replaced by the right-hand side vector of the system, which is what we call the B vector. The B vector on the right-hand side. Guys, this is basically the only new material today. The little thing in blue. So the B sub j is just, you take the original matrix A that you had in the first place, and you just swap out whatever the jth column was, and you put in this B vector that's on the right-hand side of your system. Okay? So that's the key. I'm going to practice this Cramer's rule with you in just a second. Last thing I want to say, though, before I get away from my big master list here, there is a fourth application that I also have not talked about yet, and that is that there is actually a geometry meaning to this number that is the determinant of A. There is a geometric insight for it, but I'm going to do that one later. We don't need that right now. It's really not belonging with this material. So you can expect when we get to chapter 4, I will come back and I'll explain, well, what's the geometry part of determinants, because that turns out to be helpful, a little more helpful later on. Okay, so I'll leave that for now. You don't need to worry about number 4 for our exam, for example. Just 1, 2, and 3. Is that a hand up? Please.
If determinants are so useful, why was your professor or whoever it was so against them?
Yeah, that's a good question. You should ask him that. But in his linear algebra done right book, he was very, very insistent. I think, mathematicians like challenges, and the challenge was, gee, can I do linear algebra without having to use determinants at all? And he managed to write an entire book that more or less avoided them. But I don't like to avoid tools that I have available to me, so we're gonna take full advantage of them here. Okay. But yeah, that's a really good question. All right, guys, are you ready to try a warm-up problem? This could just as well be on our exam on Thursday. This is a perfect level of a question. Notice I've gone a little bit ambitious with a 4x4 matrix. You'll notice when you look at my sample midterms that I was using some 4x4 matrices there as well. There's a reason for that, which is that if the matrix is smaller than a 4x4, then everybody can just run through the arrow method to do everything, and they don't have to use cofactor expansion, which honestly is really what you guys need to learn. The cofactor expansion is really important. And in the case of a 4x4 matrix, you have to do cofactor expansion. We do not have a simple formula for the determinant. Now, I've taught this class a lot of times. I can tell you that every time I give this first midterm, there is somebody, I hope it will be none of you, there is somebody who always tries to use an arrow method on their 4x4 matrix if I give them one. And there is no such thing. Okay, so please, somebody's going to do it, but it won't be anybody in this room, right? Somebody's going to try and do an arrow method on this matrix. You cannot do that. You cannot do that. So in this case, we really do have to stick to cofactor expansion. Before we get into that, let's just read what the question is asking for. Part A here with this matrix says, find the 2, 3 entry of A inverse. Notice I'm not asking for the entire matrix, which technically would have 16 numbers in it. I'm only asking for one specific entry. I'd like to pick off one particular number out of that inverse matrix. That's actually a little bit of a hint. That is a little bit of a hint that maybe we should use the adjoint method. Guys, if you use the Gauss-Jordan method that we learned back in chapter 2, the Gauss-Jordan method is going to give you the entire matrix as you go from left to right through those EROs. I wouldn't need to like limit you to just one entry. I'd just say find the whole A inverse, right? So if I'm asking you to pick off a specific number in this inverse matrix, it must be because this adjoint method is kind of well set up to do that, right? This adjoint method allows me to kind of zero in and pinpoint a specific entry in the matrix. So let's just see how that works. For the 2, 3, so let's just start the solution here, guys. Do this together and make sure everybody's good with it. There's some homework problems like this too, but they are all smaller than 3. They're all 3 by 3s or smaller, right? So I'm going to use the notation here. This is kind of me inventing a notation. The 2, 3 entry of A inverse. Notice if we use the adjoint formula, that's this box right here, every entry of A inverse has a denominator that is the determinant of A. I would like to write that down on the denominator. So this is a fraction, and the denominator is the determinant of A. Agreed? Now the numerator is supposed to be, well, the corresponding entry of the adjoint of A. Can somebody tell me what would be the 2, 3 entry of the adjoint of A? Gabriel.
It would be -1.
Oh, I don't want to know the number. I want to know what would be the expression for it.
Yeah, it would be that of the matrix of factors of the transpose, so it would be 3, 2.
Okay, so it's a cofactor. Guys, everything that's in this adjoint matrix is a cofactor. This is the matrix of cofactors. The issue though, careful guys, the issue is it's transposed. When you transpose a matrix, you swap the I and J values. So if I'm asking for the 2, 3 entry, I'm going to do the 3, 2 cofactor. That's very important. It switches positions there, right? And can somebody remind me on the 3, 2 cofactor, will I need to include a sign change with my cofactor for that spot? Giovanni, yes? Do you remember the little diagram I like to show this? Do you remember the thing? You start in the upper left corner with plus. This is an easy one to remember. And then you just alternate everywhere you go, left, right, up and down. It's an alternating pattern like this. And if you look at the 3, 2 position, row 3, column 2, there's a negative there. That means that this cofactor is the negative of the corresponding, what we call the minor, which is the M32. So the idea here is that we would have the negative of the minor. Now, if I had asked you for the 2, 4 entry, if I said 2, 4, this would be C of 4, 2, and there would be no negative there. You only put negatives sort of half of the time, right? Approximately half of the time. And you have to know when are you doing that. Basically, it's just when the 2 subscripts add up to an odd number. But if you don't want to remember it that way, you can just remember it visually from this little diagram right here. Questions so far? What I've done so far is just kind of set it up as to how we're going to solve the problem. Now we have to get our hands messy and do the calculation. So I've got to do a determinant of A, and I've got to do a particular minor. Let's start with the determinant of A first. Can anybody recommend how I should evaluate the determinant of this matrix A right here? Again, there's no arrow method. So what are we going to do? For a 4 by 4. Levi? Okay, great. I'm going to do cofactor expansion. I like that. And do you have we have 4 rows or 4 columns. We can use any of them. Is there one that you would prefer to use, do you think? First row looks pretty great, doesn't it? Look at all the zeros. Those zeros really make the calculation simpler. I like to put that into my solution, which row I'm using or which column I'm using. So I'm going to try to expand on row 1. As I go across row 1, let's be careful. Plus, minus, right? So the first term is plus 0, minus 0, plus 0, and then a minus 1 times the determinant of the matrix that we get when we cross off row 1 and column 4, right? Which is this little 3 by 3 matrix in the lower left corner. So I'm going to write that down. Minus 1 times the determinant of 0, 1, 3, and then -2, -3, -5, and then 4, -4, and 4. Okay? Guys, really try to show your work here, because if you make a very minor mistake, like you miscopy a number or you forget a minus sign or something, but if I can see your work and I can see that that's what happened, I won't deduct much of anything from your paper. But if you don't show your work, or if it's so disorganized that I can't follow it, and then the answer is wrong, it's very hard for me to help you at that point. So you really need to do yourself a favor, try to write this -1 times this determinant down, make it real easy to follow. Now this is a 3 by 3 determinant. How am I going to evaluate that one? The arrow method. I don't have to use the arrow method. I could do another cofactor expansion if I wanted to, but I might as well. I like using the arrow method because it's pretty easy. So for a 3 by 3, the arrow method just involves recopying the first 2 columns here, and then I just have to start doing my arrow. So let's go ahead and work this out. We have a minus, and then I'm going to use some brackets here. The number one mistake that people make with determinants is usually sign errors, because there's sometimes double and even triple negatives that sometimes come into it. So it's a minus all the way out there. Let's start doing our diagonals. The first diagonal is actually the main diagonal, and there's a 0 in it, so we have nothing there. If I shift to the right, the next diagonal has a -20. We're adding -20. And then the next diagonal actually has 3 times -2 times -4 is actually 24. That would be with a plus this time. So plus 24. And now I'm going to start doing my diagonals the opposite way, but I have to subtract these. So 4 times -3 times 3 is -36, but I'm subtracting -36. Okay, so remember the first 3 diagonals are viewed as pluses, and now these 3 are going to be minuses. The next one is 0. There's a 0 there. And then the last one is 4 times -2 times 1, which is actually -8. Give myself just a little more room here. Minus -8 for that one. Okay, and if you clean that all up, it should be negative of, let's see, 68 minus 20 is 48. So -48. If I did the calculation right. And again, that's another one where if you just messed up the addition and didn't try to get the right answer there, not going to be too bad in terms of grading that on the exam. Okay, everybody okay with this? If you need more practice, you've got 3 other rows or 4 other columns that you could cofactor expand, and just make sure you get the same answer, right? Should always be the same answer, -48. That's going to be in the denominator here. Now, I also need to figure out the numerator, which involves that 3,2 minor. So let me come over here and give myself a space to write down the 3,2 minor. So M32. To do that part, I have to cross off row 3 and column 2. So row 3 and column 2. And then I'm going to recopy what the numbers are that are still remaining. So the first row becomes 0, 0, 1. I have to kind of uncross some of this that was crossed off earlier. So the first row is 0, 0, 1. The next row is 0, 3, -3. And then the bottom row is 4, 4, 6. Okay, so this is the determinant we need to calculate now. Looking at this determinant, I could just use cofactor expansion along Well, the first row looks good. First column also looks good. I could use either the first row or the first column. That'd be one choice. So I could just use cofactor expansion. I have a question. Is this matrix triangular? Where the zeros are? It's a little bit tricky, guys. The triangle has to look like this would be an upper triangular shape with zeros in the lower left corner, right? Or if it was lower triangular, it would have to look like this shape. In other words, the hypotenuse of your triangle, can I use that word? The hypotenuse of your triangle needs to be actually on the main diagonal. And that is not the case here. This triangle, if you look at the shape of the triangle, the hypotenuse is kind of going this way. And that's not actually triangular. So this, I would say, no, this is not triangular. And so I can't just multiply the diagonal values together, right? So if it's not triangular, I could go back to the idea of cofactor expansion. Imagine you just expanded row 1. You just expand on row 1 again, or you could use the arrow method. That's the other choice. You could just use the arrow method. But if I expand on row 1, I'm going to get nothing minus nothing plus 1 times negative 12. So your answer is going to be negative 12. I won't even show much work for that one. Okay, it's pretty fast. I have a question though, because this relates to one of the problems I put on one of my sample midterms. Is there another way to get that answer besides cofactor expansion and besides the arrow method? There'd be something different we could do? Do you have an idea, Levi?
To get it in triangular form, and then use a diagonal.
Beautiful. I was hoping somebody would catch that. Yeah, guys, this is actually, although it's not triangular, it's almost triangular. If I permute rows 1 and 3, so now I'm going to write the third row first, and I'm going to leave the second row the same, and I'm going to permute the first row to the third row. Now this is triangular. And this matrix, remember, if you have a triangular matrix, the determinant is just the product of the diagonal values. It's the easiest thing in the world, right? So this one would have a determinant of 12, 4 times 3 times 1. And so then if you just remember that permuting 2 rows inserts a minus sign, the sign change, right? So then the 12 turns into negative 12, and that becomes your answer. So this is the right answer here, and we can see it like this. I think on one of my sample exams, I had a 6 by 6 matrix that was in this kind of a shape. So it was not triangular, but it was in this shape, and so you just had to, the way to do that problem was not to try to do any big calculation, but to just permute the rows to turn the matrix into a triangular one and then insert some minus signs. I actually really like that problem. It's on one of the sample exams.
Okay.
Yes.
I was a negative 12 because you said here that's 12 here.
This one is 12, this one is negative 12. The difference is, remember guys, when you permute 2 rows of a matrix, the determinant picks up a minus sign.
Oh,
Yeah,
that makes sense.
so if you go back, last week we went through a big long list of properties of determinants. And that was one of the things we talked about is how do the EROs affect the determinant? Well, this is one of the EROs, permuting. And every time you permute 2 rows of your matrix, you pick up a minus sign on that determinant. Okay, good questions. All right, everybody good so far? So let's just get to our final answer then. So this, we can maybe put it right over here in this corner. The A inverse 2 by 3 entry, what did we say? It's negative M32 divided by the determinant of A. And at this point, we have all of the numbers that we need. So negative of the M32 was negative 12. And the determinant of A was negative 48. Just plug the numbers in. And if you simplify that one, you're just going to get negative 1/4, right? Negative 1/4. That should be the answer. That is the 2-3 entry of A inverse. Make sense? Any questions here? The telltale sign that I want to use this adjoint method is that I was focusing on one specific entry of the A inverse matrix. Again, you could also find the inverse of A using the Gauss-Jordan method. But that's going to involve, finding all of A inverse is probably going to be a lot heavier work than what we had to do here. This one really wasn't that bad. Yeah. Okay. All good? I've got a part B on my little warm-up problem. I'd like to try this one as well. Here's a system of equations, and it says find Z. Okay, guys, if they ask you, this is another telltale sign, if they ask you for a specific unknown, notice they're not asking you about X or Y or W here. They're just saying find Z in this system here. So if they do that, if they ask for a specific unknown, you want to be thinking Cramer's rule. Cramer's rule. Because Cramer's rule is a formula for the specific unknowns in the system. In this case, the question is asking us to find Z. So which of the unknowns is that? Is that the first one, the second one, the third one, or the fourth one? Number 3, right? So X, Y, Z, and W. Any solution would involve all 4 of those unknowns. The Z, so let's start part B here, guys. The Z is the third unknown. In other words, I'm kind of thinking of the J value coinciding with the third unknown, that would be Z. So I'm going to make this Z as, so this is Cramer's rule, guys. This is what the engineering college told me they want the students in this class to know. So we're going to know it. Cramer's rule, the denominator is just the determinant of A, and the numerator is the determinant of B, I'll call it B3, because we're talking about the third unknown out of my system here. Good enough? Good news here, I already know the denominator. The determinant of A, we worked that out right here, actually. We got that one. So I just need to focus on the numerator here. Let's work on the determinant of B3 for a moment. This is a chance to just make sure we understand how the B3 is created. So that's what's in the blue writing over here, the blue writing. B sub 3, it's the matrix A, so it's the same as the original matrix. By the way, I don't know if you noticed, this matrix is the coefficient matrix for this system. So you're just taking this matrix, but the third column of A will be replaced by the B vector. The D vector is on the right-hand side of the equal sign. So if I look here, the B vector is actually this stuff right here. 5, 0, 0, 0. Yeah. So what I'm going to write down over here, in the third column, I'm going to put 5, 0, 0, 0. That's the B vector going into the third column. You with me? Other than that, guys, you just recopy the matrix A. Everywhere else, you just put the same numbers back in here. So on the first row, I still have a 0, 0, and a 1. The second row, I have a 0, a 1, and a -3. The third row, I have a -2, a -3, and a 2. I'm literally just copying the numbers, right? And then a 4, and a -4, and a 6. That's that. That's it. Okay, so this is going to give us the numerator of our formula for Z. I have to do this determinant right here. So far, the setup is okay? Don't be afraid to ask questions if you have any. I'm really not in a rush today. I've pretty much covered everything. We're just practicing, just reviewing a little bit. Now, to do this determinant, would anybody like to suggest a good way to move forward with it? Yes, Bishoy?
Column 3.
Yeah, let's do cofactor expansion. And I like column 3 because of all the zeros. Doesn't mean you have to use column 3. You could use any row or column that you want, but I like using column 3 because of all the zeros. So let me just write that down. I'm going to do column 3. Okay, because it can be a column. Now, if I go along this column, let's just also remember we've got our little our plus minus thing. In the third column, I've got to start with a plus and then go to a minus and then a plus and then a minus. So let's start going down. Here's the 5 with a plus, right? Times the determinant of some 3 by 3 submatrix. But then you see what happens in the rest of the third column? Minus 0, plus 0, and minus 0, right? You don't have to worry about those other terms because they're all going to get multiplied by 0. So I actually only have to find one cofactor right now. And to get the right thing, I'm just going to cross off this row and column and put down this little 3 by 3 submatrix. So 0, 1, and -3, and then -2, -3, and 2, and then 4, and -4, and 6. So this is going to be the 1, 3 cofactor, basically. Good to go? We need to use the arrow method on this. I think maybe I'll just save you the aggravation. We've already done a few arrow method calculations today. This determinant, I'll let you check it. It comes out to be -40. So if you need to practice a little more, you certainly can. But I have a feeling you guys are starting to get this down pretty well. So the 3 by 3 determinant is -40. There is a factor of 5 in front of it, but there's no additional sign changes. No other sign changes because this is a plus right here. And if you clean this up, guys, it's just -2. All right, and that is the numerator of the Z formula. So then what is Z? Z is equal to -200 divided by the determinant of A, which we already worked out, which was -48. And you could leave it like that. It does reduce to 25/6. And that would be a little bit nicer answer. But I do want to say a quick word about that. Somebody in my morning class was asking me, do we need to simplify our answers? Something like this, if you simplify it, is completely optional. I'm totally okay with this. You really don't need to simplify your answers. I know they tell you that in high school all the time. Oh, simplify your answer, simplify your answer. I'm not so much interested in that. I almost like to see it unsimplified. Like, it's almost more helpful for me to see the -200 and the -48 than to see something that was already reduced. Because after all, the -48 and the -200 came out of the 250B part of the work, right? If you simplify something and you really just make a really minor error with it, maybe I'll let it go. But if it turns into something that, oh, wow, they've got something that doesn't make sense anymore, then you'll probably be wishing you hadn't simplified it. Don't spend too much time simplifying your answers. I mean, I'm not going to kill you over that. It's not what 250B is about, but, you know, be nice to have something on the paper that's as correct as possible, I guess you could say. Okay. Questions on this? This is a good warm-up. It's a nice review of the adjoint method for A inverse, along with solving a system using Cramer's rule. Yeah, so that's some new topics here. Just wanted to show that to you. Are we good? Okay. What I'd like to do next is actually help out with the homework that's due tonight. Because it's not because I think the problems are super hard, but I just would like to kind of save you some time so that you can get this thing turned in and get moving on with the rest of your studying, which is really what I want you spending most of the next couple of days on. So I pulled up the homework. Nobody had a chance really to put any problems up on the board. Does anybody have one that they would like to ask me ahead of time here from 3.2 and 3.3? Well, I tell you what, while you're looking that up, I'm going to go ahead and just do all of 3.2 in about 5 minutes. Is that okay? 3.2, we'll just go through these. Some of you have already done them, I imagine, but there's only 4 problems in this section, and I can run through these really quick. Okay, so 38, 39, 40, and 44 from section 3.2. And let me write down what this is about. For all of these problems, the A and the B are 4x4 matrices. So they kind of give you this assumption that you have these 4x4 matrices in front of you, and then they just give you as a given that the determinant of A is 5 and the determinant of B is 3. So this is just given. They just kind of give that to you. And then they're going to ask you to find the determinant of some other matrices. So the first one on number 38, it just says find the determinant of A squared times B to the 5th. Does anybody know how to do that? Much of it. Basically, yeah, this is not any harder than you think. You're just literally plugging the numbers in. Guys, remember, determinants behave really nice with multiplication. So A times B times B times B times B times B, that's what you have there. You literally, I mean, I could write it out. I mean, I guess I'll write one step here, but you don't really, you can kind of just jump to the answer. You're just taking the determinant of A twice and the determinant of B 5 times. And that just becomes, if you just use what they gave you, 5 squared times 3 to the 5th. I don't even need you to simplify that. If you do simplify that, it's okay, but I don't care. It's almost nicer to see it just written as that multiplication. That's 38. Done deal. How about 39? 39 is very similar problem. The determinant of A inverse B squared cubed. So they want us to take A inverse, multiply it by B squared, and then cube that whole thing. Okay. So again, I'm just trying to do some of your homework with you here. Even if you've already done it, we can just kind of check the answers. But you can see that you're cubing something. So I'll just put the big cube on the outside. Can somebody help me with the determinant of A inverse? Somebody I haven't heard from yet, maybe? Thank you. Yes, Safra? 1/5, yes, just a reciprocal. Remember, the determinant of A inverse is the reciprocal of the determinant of A, which would be 1/5. And then again, we have B squared. Well, the determinant of B was 3, and we just need to square that one. So you get that as an answer. You could leave it like that. I might make this one look a little nicer if I just write it as 9/5 cubed. That would be a good way to clean it up, I guess. That's number 39. Okay, and then number 40, I'm just rolling right along. Number 40 is another property of determinants. So the determinant of 2B quantity inverse times AB transpose. So this time I'm going to multiply sort of two things together. Again, the determinant will respect that multiplication. So I can figure out the determinant just on the first part, and then I can figure out the determinant just on the second part, and then multiply them together. Okay? Let me know if I'm going too fast. For the first part, I have an inverse. So when I think about the inverse, it's like, oh, that's 1 over, right? And it's 1 over whatever the determinant of 2B is. So the question is, well, what is the determinant of 2B? I gave you the determinant of B, but what is the determinant of 2B?
6.
Not 6. Yes.
2 to the n.
2 to the 4th times 3. Yes, it is actually 2 to the 4th times 3. Let me remind everybody about this one. This one is sometimes easy to get mixed up about. If I take the determinant of a scalar multiple of a matrix, the formula for that, it is in your list of properties, so you can review it. It is k to the n power times the determinant of A. So in this case, the n is 4 because they told us that these matrices are 4 by 4 sides. So every row of our matrix is getting multiplied by that same k value. So in this case, that's a 2 to the 4th power. And it's getting multiplied by the determinant of b. Yeah.
What you're saying now, where does it, where does the 2 to the 4th come from again?
It's the k value is 2 and the n is 4. So 2 to the 4th time, this is actually, I'm applying it right now for 2b. So if I put 2b here, then this is 2 to the 4th times the determinant of b.
Oh, but I'm just saying, where did the 4 come from?
It's from right here.
Oh, that makes sense.
Yeah, the size of the matrix.
It
Yeah.
makes sense.
That's it. That's it. Good question. Everybody following that one? This is the one thing that sometimes trips people up. And I'm not done yet. I'm not done yet though, because remember, I still have A, B transpose. Ken, how does the transpose affect the determinant? Do you remember? If I permute 2 rows, that would be a sign change. But what about transpose? Byron, do you remember? Not sure? Guys, on Thursday last week, I made a list. It's like, couldn't be more crystal clear. You know what it is now? It's just the same. It's just the same, right? So guys, you need to review that. This is like determinants 101. Is like those basic properties of determinants. You gotta know those. So in the case of transpose, nothing changes, right? So in this case, that transpose does nothing. The only thing left is A times B. And the determinant of A times B, of course, that's just 5 times 3. No problem. Okay. And so this would just be, you could simplify that, I guess, 5 over 16. That'd be the answer for part C. Or for number 40, sorry. So far, so good. Let's do the last one, number 44 from this same section. Let's try to do the determinant of the matrix 4b cubed. Now, the parentheses are important. It's 4b quantity cubed. Okay. So let's think about it together. It's really 4b times 4b times 4b. So I'm just going to be cubing. I'm just going to be cubing whatever the determinant of 4b is. And what about that? To do 4b, that 4 is my k value, right? I got to power that up to the 4th power. And then multiply that by the determinant of b. Again, they gave that as 3. Now, this is going to be it. Okay? Again, I don't need you to simplify that. Like if you wrote it like that as an answer, I would give full credit for sure. No need to worry about it. The numbers are too big and you don't need to waste your exam time like that becoming a mental calculator. So just leave it kind of unsimplified. That should be good. All right, that's it for 3.2. That's the whole assignment, is just those problems right there. Let's go on and do a couple of the problems from 3.3, unless there's any questions here. The only thing I have to say is that if you are rusty on those properties of determinants, like how does transpose work? How does inverse work? How does multiplication work? How does scalar multiples work? Then go back to that list because it's all in one place. You'll have it all right there in front of you, and you can look at it all together at once. Okay, super. Let's go on to some of the problems from section 4.3. Actually, the problems from 4.3 are kind of like the warm-up that we did, except easier. Because the 4.3 problems are not 4x4 matrices like this example was here. I'm sorry, I said 4.3? I meant 3.3. I meant 3.3. Yeah, thank you. Yeah, so let's do some 3.3 questions. I'm gonna skip the first couple of them and maybe leave those to you, but let's do 43. I'll do 43 with you here, and then we'll do 3 or 4 of these, and then we'll take a little break. And 43 is a 3x3 matrix. I'm going to write it for you here. This is a matrix A, and it's -2, 3, and -1 on the first row. The second row is 2, 1, and 5. And the third row is 0, and 2, and 3. And they're gonna ask us, actually, it's a 4-part question, but really all it is ultimately find the inverse of A. But part A, they sort of do it in baby steps, and they start off by asking you to find the determinant of A first. So we'll start with that and go from there. Why don't you guys try it? Can you just work out the determinant of A while I'm erasing? And then we'll see what everybody got. Since it's a 3x3, we can just use the arrow method potentially. Jay, did you come up with an answer?
8.
Jay got 8. Did anybody else get 8? No. Okay. Well, let's see. Did anybody else get something different? Josh. -8 is another choice. Did anybody else get -8? Okay, about 4 people. Did anybody else get anything different? I would just use the arrow method on this, guys. So if I recopy the first 2 columns, right, just start drawing my diagonals. So let's just do it together. All right, the first diagonal gives me -6. The next diagonal is 0. The next diagonal is -4. And now I subtract the diagonals that go the opposite way. -0, -20, and -18. Just have to watch out for your signs. Make sure you don't have any sign errors. But this is -6, -4, that's -10. And then adding 20 to that is +10. Subtract 18, I am getting -8. -8. So there were a few people that got -8, and that looks pretty good to me. Okay? So that's just the arrow method, no big deal. The second part of the question is really where the meat of the question is, which is they ask you to write down the matrix of cofactors. Let me recopy A again. So -2, 3, -1, and then 2, 1, and 5, and then 0, 2, and 3. I recopy this matrix, and I would like to work out the matrix of cofactors for this matrix. Okay, this takes a little bit more work. They're asking for the entire matrix of cofactors, which will just be the same size as the original matrix. Generally, you don't need to show any work here. You're just going to fill the numbers in. So let's think about the 1, 1 cofactor. That's the matrix A. Can somebody tell me what would be the 1, 1 cofactor of that matrix A? Josh. -7. Does anybody else agree with that? Yeah, a lot of people agreeing with that. So if you cross off row 1 and column 1, you're just looking at this little 2x2 determinant. AD minus BC, right? 3 minus 10, that would be -7. I like it. Okay, let's move along. What about the 1, 2 cofactor? So I'm going to try to be careful about how much I'm erasing here. So go back to our original matrix. The 1, 2 cofactor is actually made up of these 4 numbers, right? Because you're crossing off the middle column and the first row. What would be the 1, 2 cofactor that's associated with this matrix? Josh?
-6.
-6. Why did you say -6?
Because it's plus, minus.
Okay, my morning class got caught on this one. You guys managed to remember that's a minus there, right? You have to do a sign change on that. So if I do that 1, 2 entry, it would have been the determinant of this 2x2 is 6, but I have to write down -6 because there's a sign change. All right, let's go a little faster. What's the 1, 3 cofactor going to be? Just this little 2x2 in the lower left corner is definitely just 4, and there's no sign change there. Great, let's go to the second row. The 2, 1 entry, so I cross off the left column and the middle row, I have these 4 numbers. What would I want to write down for my 2, 1 cofactor? That's 9 minus -2, which is 11, but I have to do a sign change. Becomes -11. Is my speed okay? Am I going too fast or too slow, or is it about right? Okay, just making sure. The middle entry, I have to cross off the middle row and column. If I look at the 4 numbers on the outside corners, what's that cofactor going to be? -2 times 3 minus nothing, right? That's -6, no sign change. Sweet. All right. Why don't I let you guys finish it? I'm gonna give you 2 minutes to finish the rest of this matrix. Try to do it right now together. This is your homework after all. Let's just do the homework all together. Some of you might have already done this, but I'll let you finish it and then I'm gonna take some volunteers. Or I might just pick on people. Sign changes are gonna just be in these 4 places where there's the negative. Sorry? Uh-huh. If it's in the positive spot, it just means don't do anything. Just leave it the way you find it. If it's in the negative, do a sign change. Yeah, that's a good point. Take 1 more minute, let you guys finish that up, and then I'm going to see what you came up with. Yeah, you can check with the person next to you. Just to make sure you've got kind of something of the same answer. If you've got a partner. Check that lower left corner again. Okay, let's see how we're doing. Amber, can you please tell me, what did you get for the 2, 3 entries? 4. Did anybody else get 4 for that? Yes? Good, yep, there's a sign change on it. It's technically a determinant of -4, but then we change it to a positive because of the sign change. That looks good. Ruben, what did you get for the lower left corner? 16. Did anybody get 16 down here? Yes, I see people nodding yes, I like that. That's just this 2 by 2 in the upper right corner. I love it. Let's go to the bottom middle corner. Giovanni, what did you come up for that one? It's a tricky one. Cross this off, cross this off. 8. Right, so you have -10 plus 2, which is -8. But what he did is he did a sign change and turned it into an 8.
Is it because of the negative?
The negative right there. That's right. That's what we're looking at. If you need to, just start off the problem drawing this little diagram out. It's kind of helpful to have that. And let's see, Osama, what did you come up with for the lower right corner of this matrix? -8. Let's check it. -2 minus 6. Yep, I like it. -8, and there's no sign change on that. Everybody agreeing with this?
So, you're saying, what is where are you saying, where does the positive come from?
The plus just means, this is just what you have to remember. The plus just means don't change the sign.
I know that, but I'm just saying on the bottom right.
Yeah, so you have -2 times 1, which is -2, subtracting 6, that's -8. So I just leave it as -8. I don't do anything to it.
And then the plus comes from the bottom right.
The plus,
Yeah, comes from the bottom right.
this is given in advance. This has nothing to do with what the matrix looks like. This is just a general rubric that you're
Because
using.
like you're saying that with like negative,
Mhm.
like for example, it's a,
Okay, in the negative, guys, really quick, I'm gonna explain this one last time. Anywhere I see a minus in this diagram, which you should draw before you even start the problem. Anywhere I see a minus in this diagram, when I calculate the 2 by 2 determinant, I'm gonna change the sign of what I get. If I get 17, I'm gonna write down -17. If I get -32, I'm gonna write down +32. And just these 4 positions only. If I'm anywhere else in this diagram, I don't do anything. to change the sign. I just leave what I got for my determinant as the answer. Yeah. Okay, so that's how we come up with the matrix of cofactors. Now, part C, let's look at part C, guys. It's asking us to find the adjoint of A. You remember how we do that? Transpose of the matrix of cofactors. This is a quick one, right? This is just M sub C transpose. So all I have to do, I'm going to write down the answer immediately. I just recopy the first row as the first column. The second row becomes the second column. And the third row becomes the third column. I can just jot that down. It is possible, if you get good at this, that you might be able to go straight to here from the original matrix. In other words, you might in your head calculate the 1-2 cofactor and then write it in the 2-1 position. I don't recommend that normally unless you're really on your A game, because then you got to remember more things all at the same time. But if you were to do that, I would accept it. Like if you didn't write down part B and this is what was on your paper, I would say, okay, they obviously transposed it while they were going along, and I would be okay with that. All right. But that's the adjoint of A. And then the last part, part D, is to find the inverse of A. And for that, we just use our adjoint formula. So 1 over the determinant was -8 in part A, times the adjoint of A. So the adjoint of A would be just recopying the matrix right here from the last part. Just recopy that. That's what it's going to look like if I did everything correctly. Hopefully I did. That's going to be the A inverse. Perfectly okay to leave your answer like that. So some people this morning, they were asking me, well, can I just do this? Can I just multiply the 1/8, the -1/8 in and write it like this? And there is absolutely nothing wrong with this. So you could do this. If you want to write that as the answer, by just feeding the -1/8 into all of the entries of the matrix, but you don't have to do that. Right? It's okay to leave the -1/8 out in front of the matrix there. So far, so good? All right, so that's another good example of this whole process. Let's go on. I'm going to do a couple more problems, then we'll take a break. All right, let's just try to get a couple more things in. Again, I'm pretty much just trying to make good on my promise to do a lot of your homework for you, so you don't have to spend more time on it. Let's do 52. 52, this is also from the homework. Again, this is much easier than the one that we did in the warm-up because it's only going to be a 3x3 matrix. Here is the matrix on number 52, guys. 2, 0, and -1. 2, 1, and 1. And 3, -1, and 0. There's the matrix A. And they would like you to find, on 52, they want you to find the 3-1 entry of A inverse. The 3-1 entry of A inverse. Right. Okay, so just to get the stage set here, I'll go ahead and start writing out my solution with you. We'll pretty quickly through this because we've practiced this already quite a bit today. But just to be really clear, one more example to practice on. Actually, just so you know, you're going to find these on the sample exam. So this is not like some problem I never asked. This has been on my exam. So basically for this, you just have to remember the determinant of A is always going on the bottom. And then on top, there's some cofactor. And you just have to remember to switch the subscripts, right? Because the cofactors are the adjoint is the transpose of the cofactor matrix. So instead of 3-1, now it becomes C of 1-3. Now, would we have a sign change on the 1-3 position? Actually, we would not, right? So if you go back to your, I should just keep this up here all the time. If I go back to my little diagram, the 1-3 position, row 1, column 3, that's a plus there. So there's no minus sign. I just simply have to change the cofactor to a minor. Right, so that's all I have to do there. Okay. I'm gonna need to find the determinant of this matrix, and again, it's simply a matter of using the arrow method if you want. I wouldn't hesitate to do that, so just recopy the first two columns here. I'll do this quickly, don't worry about showing a huge amount of work on this. The first arrow is a 0 right there. The next arrow is also a 0. And then finally, I have -1, 2, and -1, which is 2. So the first three arrows are just 0, 0, and 2. Right? And then I have to start subtracting the arrows that go the other way. So I'm subtracting -3, and then I'm subtracting -2, and then I'm subtracting 0. All of that. So that's just my arrow method. In a minute, we'll simplify that down. But that's the denominator. And then the last thing I have to do is figure out the 1, 3 minor for the numerator. 1, 3 position is right here, guys. Cross off that row and column, and we take this little 2 by 2 submatrix. I hope I'm still not going too fast. Okay, so this little submatrix is -2 minus 3, -5. Okay, so there you go. We get on top -5, and on the bottom, if I simplify that, I get 6.
A 6, or I thought that was a 7.
Oh, it's 7. 7. I said 6, I meant 7. There we go. Just checking, is everybody awake? Am I making sense, guys? Okay, good. -5 over 7, that would be the answer to 52. All right, let's do one more. You guys hanging in there with me? 59, this is also on the homework.
Oh, you mean exam?
This is from the homework assignment that's due tonight. Number 59, 2x1 minus 3x2 equals 2. And x1 plus 2x2 equals 4. They want you to solve the system, but they specifically tell you to use Cramer's rule. Okay. We have two unknowns here. They're asking us to use Cramer's rule to solve this. So that means we're going to figure out what x1 is, and then we're going to figure out what x2 is. I think I've got probably enough room to do it here. The x1, remember that the denominator always has the determinant of a on it. This seems to be everywhere. The denominators are just the determinants of a. And in the numerator, we just have to put the appropriate B matrix. So for x1, it would be B1. And for x2, it would be B2. We're just going to kind of do these side by side and kind of do them at the same time almost. The nice thing here, guys, is that the matrix A is really easy, right? It's only a 2 by 2 matrix. Just the coefficients of this little 2 by 2, just right there. So that's what goes on the bottom. What is the determinant of this matrix? 7, right? 4 minus -3 is 7. So we're putting a 7 on the bottom on both of these, right? The denominators are 7. For the numerators, well, we have to work out the B1 and the B2. Let me write B1 down right here, guys. Are we understanding how these B's work? You basically take the matrix A and you replace one of its columns with the right-hand side. In the case of B1, the right-hand side values go into column 1. So you just put the 2 and the 4 into that first column. The second column is just left the way it was originally, as before. And what do we get for the determinant of this matrix B1 right here? AD minus BC is?
This would be 18.
One more time, let's try it. 2 times 2, 4,
4.
plus 12.
Oh, that's 16.
16. Everybody got 16 on that? 16, that goes upstairs right there. So far, so good? You see what I did, Elian? So the first column got replaced with the right-hand side value. Yeah. In the case of B2, now we take the, we leave the first column of A alone, but we replace the second column of A with the 2 and the 4. And we do one more little 2 by 2 determinant. And that is going to be, what, 8 minus 2, which is 6. Just 6. Yep, that's it. And so our actual answer, remember guys, that we should really be writing this as a, a set. So I could write this answer as 16/7, comma, 6/7. And this would be an answer that you would write down. That would be a good answer. By the way, the matrix A was invertible because the determinant was not 0. Whenever that's the case, guys, whenever you have a invertible matrix, you would be expecting exactly one solution. So theoretically, thinking on the theory side for a minute, invertible matrices have a whole list of statements that go with that. You need to review this. This is the invertible matrix theorem. So an invertible matrix has full rank. Rank is n. An invertible matrix is row equivalent to the identity. An invertible matrix, if it's part of a system of equations, will give you exactly one solution every time. These things are always true when the matrix is invertible. If the matrix is not invertible, all bets are off. At that point, you can't do Cramer's rule. At that point, there is no such thing as an adjoint method for A inverse because there isn't an A inverse defined. Right? So if the matrix is not invertible, oh my gosh, chapter 3 is pretty much, there's nothing here. There's like nothing left to talk about because we can't do anything in that case. So anyway, so that's 59. This is pretty good. Help for the homework. There's a couple more that you need to do, but I should at least let you do a couple things on your own. It's more of the same. Nothing that's any harder than what we've already done. I think I might just leave that for you guys. Instead, let's do this. Let's take a 10-minute break. Let you guys kind of decompress and step outside if you want to get some fresh air or whatnot. And then we'll spend the last half hour of today's class just reviewing some stuff. I'm going to try to hit some highlights for you in terms of your studying for the midterm. So let's take 10 minutes, and then at about 2:20, slightly after 2:20, I'll be back, and we'll talk about some more stuff.
The differential equation.
She just got cheated on my last. I don't know if she was. It was like I didn't know. So she's like, she's like, definitely here. I have Instagram. Oh, okay. I didn't get it. I should at the concert started last week, I'm just like you talk to her like to the like Instagram like I have to like but when you know how he sent you like I saw my Instagram on it I'm sorry. We walked through this, like, she was just kind of like, we the whole time. She was mad. Yeah, remember? I'm not, like, they won't do it. Like that.
Now.
So bad. Yeah. I just know right now, it's kind of like messing around with a lot of people. And then on her way back home, on something, or whatever. Then we should have. Driving the whole time without TikTok. Where she wants to, bro. I can't no. She took it to my ass. I don't think she wants to. But we're friends, like friends, though. Like I'm. You told me we're friends, right? I'm not friends with them. I got this. Like, yeah, like, put that out.
Okay, yeah, so they're using that. I personally like it, but you can use whatever method you want. Okay, alright, that's fine.
Whether. And then. They're pretty close to that. Okay, like I know.
Good question on the previous.
For 32. AB minus TC. And do the algebra on it, you don't have to actually, you can't actually do it. So this is gonna take more of it. I need to pass these hands out, but you need to follow up with me, just maybe not right this second.
I can go to like.
Just use the 2x2 determinant. No PROs. No PROs.
Also a bag.
I noticed on my sample testing. It's kind of not my thing these days so much. Kind of like to. River guy or what they want to use.
No, but we
I got this on today. And that warm-up call.
Why are you so happy?
But then there might be other cases where. That it's easy to like do ER. Minutes are already like set up. So that'd be good to know.
Funny.
Yeah, that's
Maybe I can give it a season.
Yeah.
Hey, guys, I think most folks have made it back into the room by now, so I think I'd like to go ahead and get started. People feeling pretty good about that, chapter 3, the determinants? Decent anyway? Except for the arrow method. No, just kidding. Yeah, keep working on. I feel like we've done a lot of problems, like especially today, practicing that a little bit. So I'm hoping it's coming together. I have actually had quite busy office hours these last few days. And people are mostly coming in not to talk about chapter 3, but they want to talk about chapter 1. And it's interesting. It was only 3 weeks ago. Like, where did the time go? I feel like it was in my past life or whatever. It was a long time back. And so I think there's a few people feeling a little nervous about chapter 1 for our exam on Thursday. So I thought I would at least take one problem today to kind of remind you about the chapter 1. One thing that would be really good is if you could learn what's on this one sheet of paper. Most of the entire chapter 1 is summarized right here. There's not much else. There's nothing falling through the cracks. This is in Canvas. And it's in the special handouts folder. I would print this one out probably. If I have a printer, I would just get it out so it's right in front of me all the time for the next 2 days. Right? Basically, we learned how to solve 4 different kinds of differential equations. This was back in the first 2 weeks of the semester. So separable, linear, Bernoulli, and homogeneous differential equations. You will want to be able to classify which is which. And I'm just gonna tell you, if you're doing that extra credit quiz, one of the problems is I just gave a couple of differential equations and just said, hey, all you gotta do is tell me which kind it is. Right, so classifying it. So to help you do that, you have to know the form. The separable one kind of goes just explains itself. You're separating the variables on the opposite sides of the equal sign. But especially the linear and the Bernoulli form, you want to really make sure you know those. They're very similar to each other. The only real difference is on the Bernoulli equation, there is a y to the n on the right-hand side of the equal sign. Other than that, these are exactly the same thing. Exactly the same thing. And then the homogeneous of degree 0, that's the one where you attach the t's to every x and to every y, and you just make sure that you could cancel those t's right back out again, right? So that's the homogeneous one. Once you know which kind of equation you have, then you need to know how to solve it. And in this third column, I have a full explanation of all of that. Okay, so it's all in one place. All those notes you took for 2 weeks, basically, you boil it down, this is it, right? So we have to know things like integrating factors. We have to know what kind of change of variables to use. There are some equations here that you need to learn. And if you write down what you know on your exam, I will give you partial credit for that. If you just say it's Bernoulli and then you forget it, just move on, I'll give you a couple points for that. If you even tell me what the change of variables is, I can give you credit for that. So I'm going to be pretty nice about partial credit as long as you're writing stuff down, right? As long as you write stuff down. So that's important. And then on the far right column, I've got some applications here. The Newton's law of cooling and the mixing problems. There's a sample exam. One of the sample exams has a mixing problem on it. And you might notice if you look at that I actually did put the formula right there on the test. So you don't need to worry about memorizing the mixing formula differential equation because I'm basically going to give it to you. Anyway, this is just my big pitch to come back in these next 48 hours that we have. Spend some time really diving in with this. Practice some problems. Look at those sample exams. I think there's probably between the two sample exams, there's like 8 different differential equations. That ought to be more than enough to have you more than ready if you really did all of that. Not saying you have to do all of that, but if you're looking for something to do to really make sure you're solid, it is there for you to look at. Okay? I want to do just one right now with you. Since we have a little bit of time, I'd like to just practice one example just to kind of get it back into your head again and maybe help get you a little bit of confidence going into your studying. So here is a differential equation, dy over dx plus 1 over x times y equals 25x squared ln x all over 2y. The first thing you're going to want to do is think about whether this is separable, linear, Bernoulli, or homogeneous. Separable is usually a pretty tough thing to do when there's pluses and minuses and with x's and y's on both sides. It's very hard to separate these equations. Unless you can just like cross multiply everything magically, it's usually hard to get it separated. Is this one linear, by the way? No, why not, Byron?
Because of the 2y at the bottom.
The y is on the bottom on the right side. If you look at the linear form, there is no y on the right-hand side anywhere, right? So this one is not linear, but does it look kind of close to being linear? I think so, which means it's probably what? It's the Bernoulli one. Absolutely right. It is exactly in this form. This is why you need to know this form. If you know this form, you can kind of recognize, oh, this is, y prime plus p of x times y equals q of x times, this is actually y to what power? -1, right? So the first thing I would do before I even start freaking out about it, I would just write down, okay, this is Bernoulli with n equal to -1. I would just start with that, okay? That way you're getting some things written down. From there, the next thing I would recommend that you do if you get one of these, right, is I would write down the change of variables. It's on the handout. I would just put it on your solution. So u equals y to the power of 1 minus n. Okay, great. And of course, in this case, since n was -1, we can put that as y squared if we want to. So this is something you need to know, guys. You need to know it, but I'm going to give you points for knowing it. If you write it down, you'll get some credit for that. So be sure you learn that one. So u is equal to y squared. All right, the other really critical thing, if you actually want to be able to solve the problem, is you have to know what this change of variables does in converting this equation. If you remember, the change of variables will always turn the Bernoulli equation into a linear one. I said that right here. To obtain a linear differential equation. And let's write this down, because sometimes just writing it down helps us learn it better. U prime plus 1 minus n times p of x times u is equal to 1 minus n times q of x. Okay. So this one you need to know as well. It may look like it's a lot to remember, but actually the 1 minus n is really the only thing that's been inserted here from what was originally in the differential equation. There's just this 1 minus n here and here. So far, so good? Of course, in this problem, n was -1. So 1 minus n is just going to be a factor of 2. Let's write down for this problem what we end up with. We end up with u prime plus 2 times the p of x, which was already 1 over x times y. So just inserting a factor of 2, and then equals, and on the right side, we also have to put a 2 times whatever the q of x was. Guys, the q of x is sort of everything except the y part, right? So I grab everything except that y, and I'm just gonna put this here, 25 x squared ln x all over 2. I guess I could cancel the 2's on the right side. Let me just go ahead with that. That gives me 25 x squared ln of x. I think at this moment, I'm kind of done with the handout for the time being anyway. So let me give myself some room to write over there. Any questions so far, guys?
Question, so what did the two over x come from again?
Well, it was originally a 1 over x. And then this 1 minus n is equal to 2. 1 minus n is equal to 2. So 2 times 1 over x is 2 over x. Is that him?
Yeah.
Yeah, go ahead.
So wouldn't the y next to the 2 over x be y squared since we're plugging in u?
Oh, you know what? I made a mistake here. It's supposed to be, sorry, it is supposed to be 1 minus n times p of x times u. I just totally miswrote that. Sometimes I make little mistakes on purpose just to see if anybody's paying attention. Thank you for catching that. Just easy. I sort of just made a mistake. Yeah, so that should have been a u. Yeah, when you do the change of variables, all of the y's are supposed to turn into u's. And remind me one more time, what kind of differential equation has this now become? Always becomes linear, right? It's always linear. There's never a doubt about that one. So this one is linear. Let me just write it again, just so it's really right here front and center for us. So this is my linear equation. Just want to have it really easy to play with here. Okay, that's my equation. Now, when I want to solve a linear equation, the main tool that we learned how to do that with is the so-called integrating factor. So this is what we usually write as I. I'm just going to remind you, this is just the formula for this is e to the power of the integral of p of x dx. Right, so that's the integrating factor formula right here. Now, the only thing we have to be careful with is that the p of x is actually this p of x. This is not the same p of x that we started off with at the beginning. This is a new p of x for this differential equation, and it's just 2 over x dx. All right? And of course, when I want to do that integral, I can pull the 2 out, and then I can integrate 1 over x dx, and that's ln of x. Right, the integral of 1 over x dx is ln of x. Do I need to put a plus c on the end of that? We never have. Let's not start now. Okay, on the integrating factor, you don't have to do that. We're just looking for one acceptable integrating factor. The other thing we have to be able to do here, guys, or we will not be able to finish the problem, is you have to be able to simplify this. The e and the ln, they always work as inverses of each other. And I would love to cancel them out. The only thing is that before you can cancel the e with the ln, this 2 that's in front has to be pulled upstairs as an exponent of the x that's inside. So it becomes e to the ln of x squared, which just becomes x squared. That's your integrating factor. Now, unless you want to rederive how the integrating factor works on the exam, which I don't recommend, it would be good if you learned what to do with this integrating factor again. So just to remind you, since we haven't done this for a couple of weeks, what you're going to end up with, guys, is the integrating factor times whatever your unknown function is, which right now at this moment is u, in a derivative. So it's actually the derivative of that product. And what happens on the other side of the equal sign is that the q of x, which was there already, just gets multiplied by that integrating factor on the right side. So you're just really just putting the I on both sides. Okay, so this is another one. It's on that handout as well. that you would want to, you can just go ahead and write this one straight down. Of course, in my video lecture that I did on this that you watched, I derived the whole thing. But I would hate to make you do the whole derivation. We've already done that, so we can just take this one as a freebie and just work with it. Okay, so that's that. And now I'm just going to plug in what we have. The integrating factor was x squared. We have our u here with the derivative on it. And then on the right-hand side, my q of x was 25x squared ln of x. And I have to multiply that by I, and the I is just x squared. Right. So that's what we would have. And let's just clean that up as well. That's 25x to the fourth times the ln of x. And if you get this far, you're most of the way done. This is like 3/4 of the way at least to the answer. The last thing you have left to do is to try to solve for u and then ultimately replace it back in terms of y. So to solve this one for you guys, we now have to integrate. You guys have to really trust me that I'm not going to give you an integral that is very difficult at all. I mean, I haven't written the test yet, but I'm not going to be trying to do that. I want to see you do the 250b stuff. So we just integrate on the left side by just taking the derivative away. On the right side, I can pull the 25 out, but what I notice here is I'm integrating x to the fourth ln of x dx. Now, that is way too hard of an integral to just do on the fly. So actually, this one would be in the table. So remember, I'm going to have a table of integrals for you, and you should just look it up. Now, let's pretend for a minute. Let's just pretend for a minute that you made a mistake somewhere in this work. I don't know where. And you actually end up here with an integral that is really not what I planned for, and it's just not the right thing. And you find out, oh, it's not in the table, and I have no clue how to do it. If that happens to you, if you get to this integral and you're like, I don't know what to do, right? Try to just write it out. Keep solving the problem. So in other words, you can still solve this for u by just dividing by x squared, and then you can still go back and plug in the change of variables, just leaving the integral there. Okay, except for the fact that you might lose a point or two because something was obviously wrong with that integral, but don't just totally throw the problem away because you've probably done most of the 250b stuff correctly, right? And that's really what I'm going to be mostly. So try not to get too freaked out if you see something here, you're like, I don't know what to do with that. In this case, I do think I did it right, and it is in this table, and I'm just going to tell you what it is. Okay, so this integral of x to the fourth ln of x, honestly, I didn't even have it memorized myself. It's x to the fifth over 25 times the quantity of 5 ln of x minus 1, and then plus c. This time we do need to include the plus c in our final answer. So this is just coming from the table, and it's really a minor part of the problem from my perspective of the 250b. All right? So far, so good? Now we just solve for u. I'm going to be real quick about the last part. To solve for u, we just take this entire answer, 25 times the quantity of x squared over 25, times 5 ln of x minus 1 plus c. We take all of that and we divide by x squared.
Oh,
So you're just isolating the u to get the expression. Did I miscopy it?
It's x to the fifth.
Oh, it is. It is x to the fifth. Thank you. Yeah, x to the fifth over 25. Thank you. Yeah, exactly. We have that much. And finally, would this be the final answer? Not quite, because this is what u is equal to, but the original problem is for y. So I have to go back and write everything in terms of y again. But you can see, guys, that y is just the square root of u. We have it right here, yeah? I like to write this down at the beginning so that at the end I don't have to like fumble around with what the change of variables was. So if you write this down at the very start before you get into all this rest of this work, you can just look at it later at the end to make this change back. And so it's just the square root of, I'll just put ditto there, of the whole big thing that you wrote just a minute ago. And that would be great. That'd be great. Okay. I like these Bernoulli equations. You'll see them on both of the sample tests. It's partially because it involves the change of variables method and how to do the linear equations, which is really a very common type of differential equation. Sweet. Any questions? Okay, that's just one thing. I just kind of pulled something from chapter 1 just to go over it with you. What I would like to do, we only have about 10 minutes. During the break, I passed out a couple of handouts. These are the group work 4 and 5. Now, as it turns out, I've done parts of both of them already with you in class. So I don't need you to like solve all of the group work problems, but I'd like you to grab 2 or 3 other people. And I put on the board here, which of the problems would be good to look at. Now, your group isn't going to have time in 10 minutes to do them all. But I'd like you as a group to take a look at any of these problems from either of these group works and see what you can do. I'll come around and give you some pointers. And you won't finish it, but don't worry about finishing it. We're just going to try to get 10 good minutes of working together on the problems that I just passed out. So grab 2 or 3 people, grab some whiteboards. There's whiteboards all over the place. You can come to the front, the side, the back, wherever you can find some room. And I will let you go from there.